Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, and all the viewers, here my presentation entitled The Implementation of Data Depth Variance Factor for Process Control. This is the result of our research, our overseas research collaboration between Bandung Islamic University and University Utara Malaysia, with the main principal investigator is Dr. Suwanda, and as the member team, Abdul Kudus, Dr. Aceng Komarudin Mutakin, and our research partner is Professor Dr. Samsuritawati Sharif. I am very happy to present the result, and now we direct to the introduction. Okay, what is data depth? Data depth firstly initiated by Tukey, which introduced the concept of depth of location. And as we know that for the univariate variable, median is the deepest data. Yeah. We can see here, median here is the deepest data, which is the outer. The lowest or the highest is the outlier, I think, and not be the outlier, but this is the outer. For the bivariate case, here we have two variables. Yeah, let's say x and y. The depth at which the point x is the relative location in the two-dimensional data set, which is defined by the smallest number of data points located on one side on the line passing through x. That's the definition for data depth for bivariate case. And then we can further develop the concept of data depth for multivariate cases. And there are many researchers which studied the type of data depth for multivariate cases. The first one is depth of location, which is proposed by Tukey, and the depth of Mahalanobis. Then the convex hull filling depth, which is introduced by Barnett, and the depth of Oja, the simplicial depth defined by Liu, and lastly, the depth variance factor, which is introduced by our team. And in this presentation, we discuss on the two comparison between Mahalanobis depth and factor variance depth. What is the Mahalanobis depth? Let we have sample of size n, x1, x2, and xn, which is p dimension with distribution f. Then the Mahalanobis distance is expressed by the equation number 1 here. Okay, here x bar is sample mean factor, S is sample covariance vector, and a sample covariance matrix, and N is our sample size. The Mahalanobis depth has some condition. The first one is N should be greater than P. The sample size should be greater than the number of covariates, the number of variate, the dimension. The second one is the correlation between variable should be not strong. And the third one is we have to have positive definite S matrix, variant covariant matrix. And our team has introduced the variance vector depth, which is defined by equation number 2 here. And our proposal has a fewer condition, has weaker condition. The first one is sample size no need to be greater than dimension and no need to be greater than P. And the second one, we has no problem with strong correlation between variable. And the third one, the variant covariant matrix S should be positive definite. There are many implementation of data depth. The first one is to detect the outliers. The second is to control the production process. And for the process capability analysis. And then for cluster analysis. And the last one is for classification analysis. The first one, the implementation of data depth for controlling production process. There are two steps, there are two ways. The first one is for the exploration step. We can use depth plot. Okay. Then the second one, for the inferential step, we can use the plotting of depth statistic on the control chart. The first one, depth or DD plot simulation. Here we conduct a simulation study, to construct the DD plot simulation. The DD plot simulation, the objective of DD plot simulation is to compare the distribution of two populations by demonstrating the pattern of DD plot. Here, the step for the construction of DD plot. First, we have to generate the multivariate data of size M for population with F distribution function. And then, we calculate the sample mean factor and sample covariance matrix. The second one, we generate the others, data multivariate data of size n, but here from population with G distribution function. And then we calculate the mean factor and sample covariance matrix. The third step is we combine the sample data from F and from G, from first step and from the second step. And then we calculate the depth of each observation in step of 3, in the third step, using the average vector and covariance matrix of step 1. Here we can get the DF. We can get the DF. DF is the data depth for F distribution. And then the fifth step is calculate the depth of each observation in 3, the combination data using the average vector and covariance matrix step 2. And from this step we get the DG. DG is depth for distribution G. Then we plot the pair of DF and DG. If the scatter plot forms a straight line through the original point, and through the coordinate 1, 1, then we conclude that F and G are the same. Otherwise, F and G are different. Okay, let's say for the scenario number 1, we have distribution F is multivariate of port variate, yeah, multivariate with dimension 4, with a factor of mean mu F and factor of covariant and metric covariant is sigma F with this element. Then for G distribution, we generate for multivariate of dimension 4 with mean factor is mu G, which is equal to mu F, like here, and a sigma or covariant matrix G is equal to F. So for the simulation 1, F and G are the same. Okay. Then the scenario number 2, yeah, all variances increase to 2 here. This is the difference, yeah, from the first scenario. But the correlation remain the same. So the scenario number 2, the second distribution, which is G distribution, has a greater than variance element. And then the scenario number 3, F is from multivariate with dimension 4 like before, and G has a shift in first period mean factor, first element of mean factor. But the variant covariant matrix still the same. The simulation number 4, which is the scenario number 4, the mean factor and covariant matrix was changed. G from multivariate distribution with dimension 4 with mu G and sigma G, like here, yeah, like here. And for our simulation, we use M is equal to 1000 and also N is equal 1000. Okay, this is the result of our simulation. For simulation number 1, we can compare between Mahalanobis depth, the left picture, with variance vector depth, the right picture. As we know that the first simulation, both distribution F and G are identical. Yeah, we can see here that the right plot is better than left plot. Okay, this is the scatter is close to the line, straight line between original point and 1.1 here. Okay, then the scenario number 2, we can see here. Okay, we can see here. As we know that the scenario number 2, all variances increase to 2. So the G distribution has more variance, And we can see here that it shown by the picture on the right side, which is from vector variance depth. So this is better. Than Mahalanobis depth. Okay, then number 3. Number 3 is simulation with outlier for first variate here. So we can see here the difference between Mahalanobis depth and vector variance depth is shown by figure 3 here. Yeah, F and G are different in the mean vector. Then this is, I think, the simulation number 4. This is the simulation number 4. Okay, we can see here F and G are different in mean vector. Still, the data, the vector variance depth is better than Mahalanobis depth. Okay. The next implementation of the depth is to construct the Q control chart. So we construct the control chart based on vector variance. This is the step to construct the Q control chart. The first one, we have historical sample of size M, let's say Y1, Y2, and Ym, which is in the state of in control process. And then we take a sample of size N for K period. Usually N is equal to 3, 4, or 5. Let the distribution of the process is G. Okay. Then we calculate the depth of historical data with formula number 2. Okay. And we calculate the depth of process. And then we calculate the relative frequency of historical data whose depth is smaller than the depth of each process. Then we calculate the mean of value for each the process sample. And then we plot the Q value on the control chart with center line and lower control limit. We said the process is out of control if the value of Q less than LCL, lower central limit. Yeah. Okay, this is the application of Q chart in the process production of seal. The data is from Hazlui 2010. In this sample, the historical data of size M equal to 40 and process data has K 10 period, each was measured with N 4 times. And the multivariate is 4 variate with dimension 4. That is the ceiling strength X1, the bottom, the right, and the left X4. And from the data, we calculate the mean vector and the variance covariance metric. For N equal to 4 and alpha equal to 0.00273, this is in line with 3 sigma control chart. Then the control limit is obtained equal to, control limit is equal to 0.5 and lower central limit is equal to 0.1265. Okay, and here the chart, the Q chart for the data, we can see here that individual number 3 is signal to be outlier, to be out of control, and also the subject number 7 and subject number 9. Because why? Because here the lower than lower central limit. Okay, this is the Q control chart vector variance for the process seal. Okay, to see the variable that goes out of control, we can see the box plot for each of the following variable. Okay, we can see here. This is the box plot of X1. This is the box plot of X2. And then the box plot of X3 and X4. We can see here in period 3, here, this is period 3 for x1, period 3 for x2, period 3 for x3, and period 3 for x4. The variable x1, x2, and x3 appear to be diffuse, we can see here. Yeah? And then for the period of 7 here, period of 7 for x1, period 7 of x2, and then period 7 of x3, and period 7 of x4. We can see x3 is very diffuse here. x3. Okay, here. This is very what we call very scattered, because more variation here for x3 in period in the 7th period. And then in the 9th period, okay, we can see here in the 9th period, this is has variances, but here is more variation than x1, okay, and also here is smaller variance. So x3, or here x3, but I think x2 is more variation. Not only x3 for period number 9, x2 also. Okay. So the conclusion, the variant vector data depth is an alternative to Mahalanobis data depth, and we saw here that the vector variant data depth is better, which is shown by our simulation studies. And then the advantage of vector variant does not depend on the sample size. This is the what we call the advantage of our method. Okay. And then the distribution of data depth does not depend on the distribution of data. So our method is distribution free method. No need assumption of distribution of data. Then we has construct the Q control chart by using vector variance depth. And then we have applied our Q control chart vector variance in the sealing process, and so a signal that process is being interrupted. The process is out of control. So thank you for the reviewers, for the funder of this research, which is LPPM University Islam Bandung, and our research partner from UUM to make it real. Okay, thank you. Wassalamualaikum warahmatullahi wabarakatuh.